by Andrew Godwin. Andrew is a Django core developer and the primary author of both South and the new Django migrations framework. He's employed as a senior software engineer on Eventbrite's architecture team and has spent much of the past decade making databases do things they were never designed for. In his spare time, he also enjoys archery and flies private planes. Ladies and gentlemen, Andrew Godwin.
Hello everyone, and welcome to my talk. This is a sort of an interesting sort of bridging the gap between small and large companies. The idea is that scaling is a fantastic idea, but it's not for people who are sort of starting out. Like, this is how you sort of approach that topic to start with. As I was introduced very nicely, I am Andrew. I am a senior engineer at Eventbrite, where I do our architecture team. Among other things, this means making sure that we can work for the next 10 years, that we can scale to the next $10 billion of tickets and so on. And also Django core developer. And in particular, the upcoming Django 1.7 release is kind of my baby in some senses. It's finally where we've landed the 1.7 migration stuff in Django, which is kind of a port of South. For those of you familiar, it's obvious. For those who aren't, basically Django migrations are a way of changing your database tables to match your current models in Django. It's a very complex topic. I have many, many other talks. My entire speaking career has been about migrations at many points. My first one was at 2008 at DjangoCon US. So there's a lot of data on that. But this is different. This is about sort of like big data. What is big data? Is it 1,000 rows? Is it a million? Is it a billion? Is it a trillion? Like, this differs everybody. Like, I have run sites with all four of these numbers as number of rows. They all have their own challenges. Sometimes 1,000 rows is the most difficult one to do, because it can be acquisition of data, it can be very important data, it can be reliability. Sometimes a billion rows is like, if it's a billion numbers, that's trivial to store. You've got to think of the different sort of styles of stuff here. And scalable designs are always a trade-off. When you sit down and go, we're starting a brand new site, or a brand new company, or a brand new project, and we want to make this scalable, you're trading off your time now for your time later. It's technical debt, pure and simple. And at some point, if you're very sure, and you've got a guaranteed user base, which if you have, I'm very happy for you, because nobody else does, then yes, perhaps you can make that call. But there is a nice middle ground here of saying, well, we'll make the site not scalable for now, and we'll focus on features, on iteration, on making our development process much more flexible and having more iterations, but leaving the right breakpoints in there so that when we do get big, we're not backed into a corner. There's a sort of middle ground here of saying, well, these couple of key points, as long as we recognize these exist and we plan for their existence, it's kind of like a reverse technical debt. You're getting technical credit for the future. You've already put some work in. You've already planned that basic idea of, well, we'll know we'll have these problems, and then we can have them. As was famously said, premature optimization is the root of all evil, but there's a middle ground there. If you're a small company or agency, your lifeblood is change. Like, I have never seen a project where the spec was correct at the start. Even the government can't do this right, and they have billions of dollars, so we have no hope. And so you have to focus, especially as a startup as well, where you have a limited runway or limited funding. As an agency where you're working with clients' money, and they're often very thrifty, of course, because people are with their money. You have to focus on the ability to change quickly. And you don't need to scale from day one. And a big part of this is what I like to call these four main points here: rapid development, continuous deployment, correct hardware choice, and scaling breakpoints. Now, I'll cover all four of these in this presentation, but these are sort of my key things I like to point out to companies, is saying, like, this is what you should be focusing on. These are the key things you need to be looking at and making sure that you're ready for the future. Rapid development is the number one thing. This is migrations. A lot of your application's day-to-day changes are changes in schema. They are making sure that as you're changing your site, there is no overhead. It's about making the right call. If you're faced with, well, we could model this correctly, but it means 2 hours of downtime to apply the new column change, you're going to make the wrong choice. You're giving the wrong incentives to your developers. And so a very big part of this is making sure that you have all the things in place to make sure that you can change the schema rapidly. And another part of this is this sort of trend towards schemaless, which is incorrectly called NoSQL. That's a very bad term because you can have SQL schemaless stuff. But when you choose to have an explicit schema, you specify columns, you specify types, you specify relationships. It's very simple. You have this wonderful thing, say, okay, right, we have names and weights and stuff. It's fantastic. When you specify schemaless stuff, it's not schemaless. There's an implicit schema in there. When I have a document, say like MongoDB or PostgreSQL fields, I have a document in there like this. Now, sure, it's just a blob. It's just like a random dictionary of stuff. But there is an implicit schema. Your application is expecting to see a name key. It's expecting to see an ID key. And so even though it's not codified in a file or in a sort of SQL spec, your application's logic is codifying an implicit schema. And one of the problems with this is that it turns out that databases are better than you at storing data. Shocker. If you're doing all your checking logic in your application, you have to cope with all the same things your database does, with missing fields, with incorrect types. Of these 4 examples on this slide, only one of them is correct. Only this top left one here is the correct format. This one has a string there rather than an integer value. Good luck catching that. This one has, correctly, it has a string here, but oh look, the name field has actually been put in French. Damn it, we must have let a translation string somewhere in there. And this one is actually correct, but it's a negative integer. So there's a range check on that. Like you can't have negative weight unless you're in some crazy science fiction movie. But all this kind of comes up like, because you're doing all this work, because you're sitting there and giving yourself all these different constraints, at the end of the day, you're codifying all these problems in your logic. And as you change the schema, you're adding more if statements. If I add different things, if I rename the fields, if I change all the way things appear, I'm adding more and more conditionals, more and more if statements, more and more different logic to try and get around this. And you end up with clutter. Unless you go through every time you do a change and rewrite every single record in your schemaless database, which, by the way, is the point that you're not doing because otherwise it's really slow and expensive, much like column changes in databases are, then you've got this problem. And it's a problem you need to work on. So be aware that just going, do it schemaless is not a valid solution. For some things, it's perfect. For things like CMSs, where you have random stuff on pages, this makes entire sense. For things where you have a very fixed schema that you know up front and that might change 1 or 2 times, don't be so sure. Continuous deployment kind of rolls into this. Now, a big part of a site being, I hate to use the word, but agile, having fast iterations and having easy sort of development cycles is deploying all the time. If you deploy once every 3 months, you have no idea what your site's like, what you're currently doing. You need to make sure you're developing like at least once a week, if not once a day or once every few hours. At Lanyard, I think we've deployed roughly 400 to 500 a day, because that's just how things work. We did a change, pushed it out, it was all good. Part of this is having feature flags, which there's a talk yesterday that Simon and I did about feature flags that if you're interested in, sort of helps this process. But you need to sort of make sure that you are deploying all the time. And part of this is changing your schema. Now, this slide assumes you're using a standard relational database, preferably Postgres, because MySQL is not the best, as people who see my previous talks may have noticed me saying a lot. But so the basic things you want to do here are things that don't block the database. A lot of things, especially in MySQL, you change a column, they will rewrite every single storage row. So, for example, if you add a column with a default, it will make space for it, and then write the default into every single slot in every single one of your data files. It will take forever. So the key things are that on Postgres, you can add a nullable column for free. It's basically lockless. It's almost instantaneous. And even if it's not a nullable column technically, even if you're supposed to have a value in there in every single row, add it as nullable, then backfill the values in slowly over time, parallel to your application running. And then finally, when they're all done, you can remove the constraint. And that's still a check, but it's a little bit shorter. But you can do this in a multi-phase process. Like you're having to trade off simplicity, but you're gaining that flexibility, that speed, and that sort of availability at the same time. Another one thing here is that if you are without a database that can do null adding straight away, what you can do is you can add a new table with a one-to-one relationship and backfill the values that way. You kind of increase the number of queries. You're trading off initial time here for later query time in the application, which could be valuable, could be terrible. But it's an interesting way of like hanging off a lot of new data off a very, very popular solver model. Eventbrite has a couple of these because we have a big MySQL database where adding a column would take around 2 days. And so we have a few sort of one-to-one tables that we're like, well, for now we can do this. And because they're in about 10% of events, it's not that big a database hit. Finally, work out what type changes your database can do without any touching at all. In particular, I believe if you shrink the length of the char field, that doesn't require rewriting. If you grow it, it does, because it has to have new space. But if you shrink the length of it, that's fine. Similarly, you can convert certain types to other ones, depending on the back end, for relatively low cost, because they are represented the same or in less bytes on the disk. But that's kind of a tricky one to do. In some cases, it's impossible. But things like, like on Postgres, changing text to string at some point is almost interchangeable too. Hardware choice. It's a big bugger of mine. The cloud. It's wonderful. It's mystical. It's kind of a lie. The cloud is wonderful if you don't have sysadmins for about 3 or 4 months. I mean, so don't get me wrong, I love not having to go down to the data center at 4 in the morning and swap disks. That's fantastic. But I get that with co-location with remote hands. I get that with dedicated servers, with a lot of other stuff. And the problem that is VMs, so Amazon EC2 or even your own stuff, are terrible at disk I/O. Databases really suffer on virtual machines. They all still work, obviously, and things are improving. We have a thing called DTD now, which helps I/O a little bit, but they're still a lot worse than, like, say, memory or CPU usage. And your database is obviously going to be doing a lot of I/O. So one of the things you can do is stick your database on this nice big box with disks, SSDs if you want to, because they're quite cheap these days, and you will see a very decent increase in speed out of that. Another part of that is memory is king. Don't run your database with anything else at the same time. Like, databases kind of rely on having cache and memory lying around they can use. Like, they're optimizing themselves as patterns. If you run, say, Postgres and like Solr and Redis and a few other things in the same box, they're all going to be clashing and sort of having the wrong stuff and overwriting it to memory, and you'll just get worse performance. Like, make sure they're nice and by themselves, a nice little bubble, and sort of have the right idea what they're doing, and you'll be a lot better off. Another sort of cheap trick that I learned running, I used to run a site called Minecraft Forums, you may or may not have heard of. It at one point got 350 million views a month, something like that. It was a lot of traffic, but that all ran off a single box. The power of adding more power is amazing at many points. That single box admittedly had 32 gigabytes of RAM, more cores than I could shake a stick at and other things, but it was amazing. Like, we just added more power, and at some point that was enough to keep up. It was very read-heavy traffic, it was fine. But if you're a small company and you've got a lot of problems with your sort of throughput in your database, don't think you have to go, oh no, we need to shard, or we need to have like this complex replication system. You can probably buy yourselves a lot of time by just upping the size of your server for a good number of years. At the point you hit the top-end server, you've probably got a decent ops and architecture team in place anyway. Another cheap thing you can do is add a read-only replica. So if you've got a lot of read traffic, just have a replica of your database that sort of streams from it, and then put all your reads on that replica. It's a very simple pattern. It's worked for many companies for many years. The only catch is that there's replication lag. So if you write on a page, just sticky that page to the master sort of replica for that page load, if you're doing web application, for example. And then on the next one, you can use the replica again. But just make sure that you're sticking when you're doing writes, so things are inconsistent, and you're fine. But the key thing here, as I was saying at the beginning, is scaling breakpoints. Like, there are a lot of nice little things you can consider now that, well, things that go into companies and see, like, well, this one small change, this one weird trick would fix this thing in 3 years' time. Like, it's one of those things that you sort of grow as you become a sort of architect and ops person. You've seen this stuff before. It's kind of like pattern matching almost. It's not as hard as it sounds. But the three things I like to look at, I've given them sort of arbitrary names here: a sharding point, a vertical split, and consistency leeway. I will explain them. They're pointless words. Sharding point. This is where you have a data set that's obviously partitionable into shards. Eventbrite has one of these. It's called events. Events have tickets, they have users, orders. They're all separated into a nice little world by each event. There's not much interpollination. And so if you see that pattern of, well, you know, we have many tables here, but these sets of data are all grouped by these sort of overarching ideas. So for example, on a forum, you know, different forum subforums could be a good way to shard. There's not many of them. But things like, say, Flickr, you've got user accounts posted on it. You can shard by user account. There's all these different things. And the key thing here is to make sure that you don't break out of that abstraction by accident. If you suddenly interlink between things, so for example, if we suddenly had like an interlink event right between different events that was quite strongly done on the website, we would break some of this abstraction. We would suddenly have thrown away all that work we've been gaining over the last 5-7 years by having that in place. And so just be aware that if you have these nice little sort of isolated sets, that's really good. Try and keep them a little bit sort of isolated. Try and keep your models nice and rounded and pure. And then the nice thing here is there's an easy migration plan. If you want to shard, there are sort of a couple of steps here that's pretty easy. First of all, there's more than one way to shard. This is my preferred way. It is not the only way. There is at least another major way of doing it. But what you want to do is take your primary key, implement consistent hashing, so it's randomized. If you just shard by it like incrementing integer, it won't be sort of it won't be randomly distributed or uniformly anyway. So you want like a good hash with a good uniform distribution, so it's all like sort of properly separated. Then you invent a large number of logical shards. Let's say 2048 because we like powers of 2. And then what you do is you map each of those different primary key hashes into different buckets, often by prefix or by sort of first number of bytes. And then what you do is you have a mapping of logical shards to physical shards. This is how things like React work, for example. So you say that at the moment when we first do this, all of our logical shards are actually on this one database. And actually, it's the one you were using all along. It's the same database. So all you're doing is writing application logic code. Nothing has changed. The database is unchanged entirely. And then it thinks it's sharding. Then when you want to migrate a shard, you turn on a replica, let it replicate the data across, and suddenly you split down and say, okay, shards 1 to 2023 are on this server, shards 1024 to 2048 are on this server, and then you can cut the replication off, and then you have 2 copies. And then just delete the old ones that shouldn't be there, and you have a sharded system. And you can keep doing this. It's not perfect, but it's a good way of starting out. Vertical split is a different kind of approach to the same problem. This is where you don't have groups of things across tables, but you have entirely separate tables. For example, if you have a ticketing system as well as your main website, they're separate. They should be different databases. And the key thing here is that having different write loads on a database server is bad. If you've got a very, very write-heavy load on a database and a very read-heavy load on the database, so like say write-heavy could be like ad tracking, read-heavy could be like reading forum posts, those are conflicting. They're sort of hitting the wrong parts of the server. If you separate them out, they're going to be a lot happier by themselves. Like databases like doing one kind of thing generally. Like for example, if you have a database row with like one field updated a lot, but the rest of the fields are very static, you probably want to pull that out to a new table because it's a different kind of data load. But what you can do here is very simple. You can move the tables to a new server. And similarly, the replication trick works here as well. Replicate the servers, and then cut down the replication when it's up to date, and then point the new table at the new server. In Django, we have routers for this. It's pretty simple. Other web frameworks have other methods too. You can even do it yourself. It's not that difficult. But you can sort of do that. If you don't want to do that, you can make the new back. So if you, for example, if you're changing kind of database, so say I've got these things, they should be stored probably in a key value store rather than an RDMMS. Then you instead backfill the new data store, and you have sort of a proxy service thing that will say, okay, I look for this thing, and you first go and check the new data store, and then the old one, and backfill, and then you come back again. And then you sort of set that going, set the backfill rolling slowly, and always write to the new database, and then eventually you fully backfilled, you can cut the old one off, and you're moved over. So it's kind of all of these different things, like sort of 2 or 3 step processes that, as long as you understand them, and you're on top of them, and you practice them, practice makes perfect, you can do this pretty easily. Denormalization is kind of a little bit just before consistency here. So denormalization is not free. It's very close to free. It is not free, like graphite. Graphite's very close to free, but not. So denormalization is one of those things where, it's an obvious thing. You have this wonderfully normalized thing, like your tutor taught you at university, or like the book you've been reading said, that everything is in one place. There's a wonderful, perfect record of everything. It's great. Unfortunately, it's not fast. You have to do like 4 or 5 joins to find all these results. It's awful. And so you want to pull things like pull the username into the forum post record. So when you're showing the forum post, you can, rather than saying join forum post with users, you just read the forum post and all the data you want is there. You can render the entire sort of div with one query. The way to do this is basically you just add the placeholder fields, again with null, never add with defaults, add with null, and then you have the app code that looks for that stuff, look for the field. If it's empty, go and fetch it with the join, then fill in the field, then come back and return it, much like you saw in the previous pattern. And then you can backfill on the background. And then slowly over time, as you save new stuff and as you run the backfill, you'll get up to date, and then you can suddenly have denormalization. And the best thing is you can leave this code in place in this case, because if you suddenly find an inconsistency or a bug that's been going for several months, you can wipe the denormalized column clean, and you'll suffer like a day or two of slowness as it backfills, but you'll get there. It'll be a lot better in the end. Finally, consistency. Now this is the be-all and end-all of scaling. At some point, you end up going, well, we need to be distributed. And distributed means you basically run into something called the CAP theorem. The CAP theorem isn't really a proper it's a properly proven theorem, but it's not technically applied to everything. But it says that you have 3 things: consistency, so that you can read the same data from everywhere at once, availability, that you can always read data without blocking, and partition tolerance, that if you split the network and rejoin it, things will survive. And the general consensus is that you can only have 2 of these at once. So you can be CA, AP, or CP. Things that claim to be all 3, by the way, take it with a very large pinch of salt, because they're probably not. And often they don't realize this yet. They just think they're fine until generally, there's a great series called Call Me Maybe coming in a moment, where this guy proves, using wonderful proof mechanisms, that all of these things that claim to be wonderful are actually massively failing. It's really quite good. You should go read it. But one of these things here is that you probably want to drop consistency. Most applications can lose a bit of consistency much more than they can lose availability or partition tolerance. And so there's no real migration plan here. This is a much more specific thing based on you, your application, how things work. But you need to work out what in your site you can take being inconsistent. What things don't matter if they're, say, 10 seconds or a minute out of date. And for example, on Lanyard, our search index is roughly 2 minutes out of date. People don't care. Like, they don't update a thing, go, it must be in the search index, and jump over to the search index straight away. That's not what happens. But if you edited this event and then you came back to the same page again, and we showed you the wrong name in the page, you'd be like, huh? So like, there's different things here. Like, you have to work out what can be inconsistent and what can't be. And not only that, you should be talking to your product people, your designers. Like, this is not an engineering problem. At some point, your entire site must be ready to deal with the fact that this data could be a little odd. Look at Google. The number of results Google shows you is a massive lie. I'm sure some of you have seen this. Like, it says, oh, there's about 3 million results. If you ever got to the end of that list, you'd find there wouldn't be. But it turns out that counting all the results takes way longer than showing you the first page. And so they say, oh, well, we have an inconsistent count. They don't mind. You don't mind. You're not calling them out and like, you said there are 3.5 million. There's only 3 million there. This is wrong. I want my money back. You're not paying the money. But you need to work that out and sort of work through and work out what you can drop. So for a good example, like, in Eventbrite, we cannot drop consistency on ticketing. If you bought tickets and they suddenly weren't there, that would be awful. We just can't do that. But at the same time, like, if an organizer updates an event's description and you don't see it for 2 minutes, that's probably fine. Like, there's a small delay there. Like, they weren't expecting you to see it straight away. And so you could pick and choose and see what you're meant to be doing. But the key thing here is that big data isn't one thing. If you've got if you're storing like giant multi-terabyte scientific research files, big data is probably having 10 of them, like trying to get them all on, like even in one thing in memory. If you've got really complex queries trying to find friend relationships to graphs or like 3 degrees separation, then it's not even the number of nodes, it's like just the exponential increase in trying to find those graph traversals. If you've got a lot of throughput, it doesn't matter what you have, like if you're trying to get like 20,000 requests a second through, anything's going to be difficult. And even then, like a lot of things are latency. Like, I can store anything you like in a perfectly distributed system if you want to deal with a day of latency to do all the queries. Like, we can just latency solves all problems, but you probably want it to not return in a day. That seems unusable for most web browsers. Perhaps you're on the moon, it'd be fine. So like, you've got to sort of work through these kind of things. And focus on your current problems. A lot of companies sit there and try and work through and go, okay, we're going to be big. We're going to be the biggest thing since sliced bread and Facebook. And so what we need to do is scale, so we have this perfect architecture that will work for 4 billion users. And of course, what they do is they spend all their time writing this wonderful system, no time writing features, no time writing actual things people want, no time doing user testing, and then they die because they've got wonderful architecture and no one to use it. I've been guilty of this sometimes. And so, this is more of a business thing, but like, focus on problems you have now, even in databases, before the ones you have in the future. Like, don't go, but what if we get all this stuff? Like, so like, Lanyard's organization stuff we know has a problem. Like, if you have more than, say, 1,000 people, it gets quite slow. But we know none of our organizations currently have more than 1,000 people, so it's fine. And we have that debt. We know that debt. Like, it's a technical debt you know about is fine, as long as you're ready to pay it back when you get it up front. It's the hidden technical debt that's the problem. And as long as you have hidden stuff, you're generally all right. But yeah, efficiency, iterating fast matters. The smaller you are, the less funding you have, the less time you have, the more that time you get back from doing this quick stuff works really well. And I think the final thing here, a big bugbear of mine, is good architecture affects your product. If your product people, if your designers say, no, product is not an engineering thing, I personally would say they are wrong. I think that part of a good product is speed, and part of speed is engineering and architecture. If you can say, we can make this number slightly less accurate, and we can move this thing over here, or we can show this 1 second later, and we can make the whole site 10 times faster, your product people say yes. often you're not even in those meetings. And so like try and have those conversations where, you know, like at Lanyard, like Dan, our designer, we'd say, oh, Dan, can we do this thing a little bit? Like, yeah, sure. Like he doesn't care that much. Like he cares that it looks good, but he's not, the design he's given you isn't like his perfect final design. It's not how it works. Like they're willing to iterate and make changes too. You just need to talk to them. So please just remember that architecture is not just about engineering, it's about product design, it's about the two of them together. Yes, thank you very much.
Any questions?
Questions? This one over there.
I just for the last thing you say, you know you have a problem with the organization structure with 1,000 users or whatever. If you don't have any customers that have 1,000 users, how did you find that problem, or what did you use to find that problem before it's happened?
It's not even that. It's that like when you're writing it, you're doing it in a way where we know this query is like n squared, and we know that when n squared hits this boundary is around 1,000. Like we've tested it obviously when we're writing it, but because you've identified that up front, because you're writing it like I'm good enough at this point. Hopefully, I'm not that good, but I'm good enough to know that I'm writing an n squared or n cubed algorithm and go, this is not going to be great with like over certain amounts. But the brute force computers means that you can generally get around that initially. So we know it's there because we identified that we know this is a bad pattern, but the option is something so much worse. But like time saves over runtime at this point.
No more questions? All right. Oh, here we go.
Is there a good paradigm in code where you can account for slave lag?
No. So the master-slave replication thing is just a small version of consistency in the end. Like you're doing a much more controlled version of an inconsistent system. But the nice thing that you can pin to the master if you have to. The best, like with websites, you've got this get out of jail free card where you can pin that one request to the master, and then by the time the next request comes around, it's probably fine. An event might be pinned for 10 seconds rather than just one page, because that's better. But yeah, you have to watch your slave lag and make sure that it is below what you expect. Like an Eventbrite, our ops team continuously watch replication lag. If it comes back, I think it's like 3 or 4 seconds, they get very panicky because if it goes over 10 seconds, the site stops working properly. So you've got to make sure you're cognizant of that difference and what happens if the two go the wrong way around. But as long as you're aware of that and you have sort of the basic pinning stuff, you can get a long way with very little code.
All right, a big thank you to Andrew Godwin.